Yaskawa.
Good morning, this is Kevin Hull, and I have with me Hunter Stoffren today. This is another webinar regarding our toolbox offerings. And today we're going to be introducing a new toolbox to the group called the Comm Toolbox, and in particular some of its functions related to command streaming. If you were to start a new project, you can simply insert the Comm Toolbox. It's version 201. Okay, but that's not enough to use the toolbox. Let's talk about the other things required. If I try to use the toolbox, you'll see that there's going to be some errors. So I'll just briefly drop one of the function blocks here. I'll connect a variable to the var in out just to satisfy that condition. But if I compile, I've got several issues to think about here. And that's because these data types are not declared. If we look at the help file, which is also updated and part of the toolbox installer, just right-click on the function blocks, it pulls up the help file. For the Communications Toolbox, we have a couple of new sections we've added called Getting Started, and it lists the other required firmware libraries or user libraries that this particular toolbox relies on. So we can see we need to add Y-Device-Com firmware library, of course, and also the Procon OS firmware library, and also the Yaskawa toolbox. These data types are actually defined in the Yaskawa toolbox in this case. So that's Yaskawa Toolbox 204 is the most recent version that would be in that installer. The Y-Device-Com firmware library. And also Procon OS. And let's see what happens now if I compile. One problem. Oh yes, Access Ref. That's kind of a small side effect issue. You'll most likely be using this toolbox with some motion functions, and so at some point you will have the motion info types defined by using PLC Open Toolbox, and that brings us down to this other toolbox I introduced, the Data Types Toolbox, that now contains all of the firmware library data type file, the data type definitions. So if I include that one as well, we will be satisfying all the conditions. And I got worse. I got more errors, and that is because I haven't deleted these default data types. Now this is part of our moving forward plan to make this easier. In the future release of MotionWorks IEC, we're actually going to include the PLC Open and Data Types Toolbox as a new project template, and these data type files will also be removed from the template. So your starting point of a new project will be in a more readied state to minimize these initial compiling errors that we have. So there we go, zero errors and only 4 warnings. And that's the process of installing the new Comm Toolbox. All right, so just a brief summary again on the command stream functions. There's about 6 different functions that are part of the Comm Toolbox to make this work, and we'll kind of graphically represent those here in a couple slides before we go into the demonstration. So overall, there's a communications manager, and this is kind of in order here on the screen. So the communications channel is part of that encompassing POU, and that helps us set up the IP address, the port number, buffer size, and some other configuration data, and a way to enable and disable this entire command listening feature. And the other 4 functions listed here are kind of lower level bits that help the whole thing work. And I guess most importantly in here you'll see is the command processor, because that is where customization is required by you to make this feature work according to the command set that you want to implement or is existing previously on your PC software. So, I mean, one of the important reasons this was developed is sometimes people have a retrofit system or they have an existing PC software program that sends ASCII commands, either serial or Ethernet in fact, and they want to minimize the rework on that side and just replicate a controller or replace a controller and program it to adhere to what was previously developed on the PC. So here's a block diagram to kind of emphasize that point. So let's say at the left side we have a PC or other device, and using some application program, we can use these tools that are part of that programming language, let's say, that was used. It could be WinSock, it could be system.net.sockets if you're using Visual Studio or C or C#, let's say. And the real goal is simply to send an ASCII string, a command that you've created or developed, and send this simple message over to the MPIEC controller and have it converted into some usable data in the IEC application program such that you can operate the machinery. And so that's what the middle piece will do for you, the Communications Toolbox. We will be able to configure the function blocks of Y-Device-Com to accept that message and bring it through some data structures to parse it and identify the command and identify by delimiters, identify the different parameters that were sent over. And part of that is customized by you, but those tools we mentioned on the previous screen, the get command and get parameter function blocks will take this apart and deliver each of those individual values that you can populate into a structure. So it's kind of identified right here as the heart of everything that you'll have to customize is in the command processor. And in a sense, that'll be a large case statement containing all the commands that you need to recognize and respond to. So I've given a couple of block diagrams describing kind of the flow of data for the command stream features, and I've mentioned that there's some customization required. And that's mainly because of you having to add your own command set to the command processor's case statement. And also, you'll have some, if I back up, you'll have some machine struct that you'll make. Actually, I'll go forward and show that. You'll have a machine struct of some kind that you'll attach to your motion functions. And because you'll need to customize that, you'll need to change the data type definition of 2 of these function blocks, 2 of the 6 or so that we show. So there's a communications manager, and there's minimal customization there other than the data type definition, because this block does contain, or this POU does contain the command processor. And then mostly the case statement here is where the major customization takes place. Everything else can remain in the toolbox and leave the code as is, and should work fine. And so finally, just another way to look at what we've got here, and it's simply a tool to take in a configuration, which is whether we're using Ethernet or serial port. Serial port is available if you use the 218 IF card or Ethernet. And we have to define a buffer size and then send the command data from the PC application. And we basically take that through the functions and convert it to a structure of machine data. So without further ado, actually there is further ado. Let's look at there's one tip we have here for you, and that is the ControllerInfo struct, which is at a specific memory address in the controller's global variable space. And this is defined, you can read this in the data types file for ControllerInfo. This ControllerInfo struct contains various information about the controller hardware. There's firmware versions, there's the MAC address. I think it talks about number of defined axes, possibly in machine data. But our focus here, and what helped us with this command streaming feature, was the fact that the IP addresses of each of the hardware interfaces are listed. You may, in theory, have more than one Ethernet IP address on the controller, like possibly if it was the MP2600, or if you did add or include some 218 IF cards to an MP2300 or MP3200. Now there's more than one physical Ethernet connector in the system, and you need to specify which of these hardware devices you're expecting to listen for the command streams from. So if that is a variable, even if there's only one, this is still useful. We can automatically get the controller's own IP address and populate it into a structure in an initialization POU. So because we know this ControllerInfo struct has all the bytes that contain the IP address of the controller. These are ASCII bytes of like maybe 192.168. I think the two E's are the dots here in hex. We can use this buff to string function block and point it at this structure and tell it how many bytes to copy over. So that's 15 bytes worth would be the complete IP address here. And it populates that byte array, converts it into a string variable, which is the IP address as a string. So as long as that function block completed successfully and the done output is on, we can copy its output to this variable. And then from there, we can actually copy it again into this Comm Config struct, which is used by the communication manager. And that's convenient because if this code is run on different controllers with different IP addresses, there's no need to go in here and hard code or change the IP address. So if you recall the list of functions and the one POU from the Comm Toolbox, the main feature of the main POU was the Communications Manager, which I've copied and pasted into my project and renamed. And that simply contains some code to run the entire function as a whole. And we've simply put in here, if there's an error of any kind, it shuts down after 4 seconds and restarts. It comes back up. So this is kind of a suggested template of some sort that's worked well for us in the applications we've done so far. And at first we're simply, we're enabled right now, and we're simply listening. So this coming on and using the Y-device-com function blocks, we're listening for information from the outside world now. And we've configured that in the initialization POU. And here's the real live code of what I just showed in the screenshot about the buff to string and the IP address being populated into this configuration structure. So we're specifying the COM type is Ethernet. There's an enumerated type for that, but 1 means serial and 2 means Ethernet. And you also have to decide on a port number, and that's just an agreed upon value that two sides of a communications activity are using the same number, so that we know that if a PC sends a message and they want to connect to the IP, to the MPIEC using port 1201, the system knows to direct that information and that communication up to this communications manager and not to somewhere else like the Modbus area or something. So this is how we keep the different protocols straight. In fact, some people have actually used multiple communication managers for, let's say, 1 per axis was their design. And you could increment the port numbers here And from that point forward, you could know that because data came on a certain channel, it's for a certain access without having to decipher that later on, such as one of the parameters of your commands. It would already be a known fact based on the handle at which it came in. Okay, so we're listening for information. We don't care who it's coming from. You know, we're not particular on the IP address that actually sends us the data. But if any message comes in from port 1201 or for port 1201, the functions inside the command channel will pick that up. And the essence of this function block is, right now we are listening So right now the essence is these two functions from the Y-Device Comm firmware library. So we are listening for a connection. When that happens, we will have a data socket, and we will know the IP address of the device that connected to us. And I'll show that happen right now. I have a Visual Basic program. See if I can show these both at the same time. So my controller IP address is 192.168.207.228, and the initialization in this Visual Basic program is setting the port number to 1201. So if I press my connect button, we're going to see that this will change state here and we'll have a data socket. Yep. So we stopped listening. This is kind of set up as a one-for-one communication, so it's kind of making a link between one sender and one receiver, so to speak. It's not really a master-slave scenario, but other implementations could be designed where you could have multiple external devices connecting to a single port, but that doesn't really make sense for a command streaming application where it would be confusing to have multiple PCs sending commands for which the controller would be expected to respond to. This is the IP address of my PC here, and this is just an arbitrary number that's now used with other functions in here to collect the data. So beyond that, you can see the behavior is such that I have some enable, disable features. We're showing some status. Lights change state as we do that. I'll show you the code behind these buttons in a moment. We've made up a simple command interface, which anyone can make their own custom command interface and use that as well. So we're getting some information back, obviously. We have two real axes on the demo kit. There's a virtual axis defined, and there is no such thing as axis 4. So that's why we actually show an error bit and a alarm ID, which is 4625, which if you're familiar with programming in the OceanWorks IEC environment means that the axis ref is not defined. So I got a jog function here. I'm jogging axis 1. If you look at the lower left of the Visual Basic demonstration screen, you can see that the speed is the velocity is about 100 now. And the position is counting up. I'm holding the jog plus button down. If I let go of it, the axis decells to a stop. It's got a slow deceleration rate. Okay, so let's take a quick look at what was customized in the command processor. And you can see how this just changed state. Maybe you saw that happen. I stopped the Visual Basic program, so it stopped communicating. And just a moment later, we lost the data socket, and the listening socket turned back on. So in the command processor, mainly, we've added some comments here to show the upper and lower area where you're expected to add the commands to be collected, and this would be it. So I showed you the enable of the servos, so that's EN, and we had a parameter on there, EN1 or EN0, to enable or disable the servos. I also did the jog command, And we'll see that in a moment on the VB side. That had some parameters with it too, to specify the jog speed. Kind of the essence or the core of what we've created here really is centered around having a two-letter command followed by optional parameters that are separated by delimiters. And that works best in the IEC code, we think, because a two-letter ASCII command can be rather easily converted into an integer, which is very convenient with a case statement. And so that's kind of what we centered most of this code around. And there's you could send other command strings and decipher them using other codes. There's other command parsing functions or instructions that could be used, but I think this is most efficient, and you get a wide range of commands you could create this way. It's a little tricky yet simple at the same time. Where did this number come from? This 16706. This is the capital AB in ASCII converted to an integer. And so you would simply take the ASCII value of A. So the ASCII value of uppercase A is 65 in decimal. If you look at an ASCII chart, and now you have to bit shift it over 1 byte. So it's the upper or the most significant byte of an integer. So you would take 65 times 256 or hex 100 to bit shift it over, and then you take the ASCII value of capital B, which is 66, and simply add the 66 to that previous calculation, and the answer is 16,706. So we basically usually end up doing this in an Excel sheet. Just it's a nice way to make a list of the commands you want to support on both sides, the PC and MotionWorks IEC. And then that way there's no confusion as to what the code should be when you're in here making your case statement. So here's some of the Visual Basic code. If I were to click on, for example, the connect button, we can see where that is here in the code. And we're using WinSock, and we're taking the IP address from the text box. It's no big deal. We have the remote port, which is hard-coded at some arbitrary number. It could be any number, mostly any number. There's recommended numbers to use by the, I don't know if it's the, I'm not sure what society that is that allocates numbers for different purposes, but anything higher than 45,000 is pretty open for general purpose communications typically. And here's some of the other commands. It's as simple as this. Single line to send the enable 0, which disables the servo, in fact, because I have a little parameter here of disable. And then a delimiter. We use the carriage return in line feed, although you can specify that in the Comm Toolbox configuration to be any different delimiters you want to use, up to 4 characters. You can also specify what character you're going to use as the parameter delimiter. So that's pretty much the main part of all this. Here's the opposite, EN1. We did some further digging. We can see that we relied on some of the events of the objects on the screen. So if I do a jog, when the mouse goes down, we send out jog, 1 to start the jog. This is also the speed from the text box. So we have JG, 1, 100, and it sends the speed over as well. And then when I let go of the button and mouse goes up, we send the stop command. I think we're specifying the axis to stop. That's a hard-coded value, and also the deceleration rate. So most of this Comm Toolbox is about command streaming from the PC device over to the controller, and we really have no tools in the toolbox to send data back to the PC. That's kind of easy to do once the PC software has initiated the connection, and there's many ways to do that as well, and I'll show you one example of what we've done here that works out nice. Okay, so we want to send all those positions, velocities, and torques back to the PC software so it can have some status information about what the controller is doing. So we start with simply using the read axis positions and speed function blocks for the different axes, and putting those numbers into a structure. I call it a monitor structure in this case. So we're populating a structure. Here is the definition of that structure. It is a monitor data. I'm sorry, it's a monitor struct, which has an array of axes, monitor array, the position, the velocity, the torque. We also have some error IDs, some enable status, alarm, and that's basically it. I think we can see it in the watch window even. So we can actually send this structure, monitor, out over the Ethernet socket quite easily. And so if we look back at the communications manager, which was the overall POU, we just tacked on a Y-write device function block, connected the command socket to it, which is right now shut off. But every time this toggles, we'll send a monitor structure out. I reconnect, you'll see that turn on. See the data updating here. You can see the command socket came back on, and every time this flashes, you can see it sends out 135 bytes. So that is the size of that monitor struct. And we did some math here to keep track of that. There's advantages and disadvantages of sending the data out this way. I mean, as opposed to other ways you could communicate with the controller, such as the Modbus or Ethernet IP, where you'd have to manage the Modbus registers and keep track of those. By simply sending the IEC structure, there's no need to worry about any of the addresses of any other communication protocol, and it's also in binary format, so there is no, these are not ASCII values as the commands were coming in. This is simply binary data, the LReal values or integer values of this information. So there's more efficiency there in terms of not having to convert to ASCII numbers and then reconvert it on the PC side. The complicated part of it is you have to know how each device lays out the memory, and mainly that's the same on Visual Basic and on the IEC controller. There are some small differences which are very important, such as we realize the IEC controller is allocating an entire byte for each Boolean data variable, but on the Visual Basic side it actually defines an integer for every bool that you make. So to keep in sync with that, when we send the data over, we added padding bytes which don't do anything, and that way all the data stays in alignment. And that's really nice, and it's really fast, and it's very convenient then for coding on the Visual Basic side. Because now we just take advantage of the WinSock event data arrival. So anytime data arrives back from that Y-write device function block, we get the data and put it into an input buffer. And then from there, we copy that over to the monitor struct, which is identical to the one that was defined on the IEC side. That's over here. So we have the exact same structure. So the data from one side gets nicely laid over on the other side here. And now it's very handy because we can simply use the information as we go in the coding to fill in the text boxes for the speed and what have you.
The code is roughly the same on this side, so there's no real use in showing it. And then I have another example that's even further customized, and it actually, instead of sending back the monitor struct, it takes data and sends back an ASCII response to a command. So I can demonstrate that. Connect. This is a different controller, address 200, and I'm connecting to port 50,007. Let's see, I want to enable the module, just like the other code. In this example, PU, power up, is the ASCII command. And on this one, it will not allow me to power up because I have not set some module parameters that are needed for stops and moves later on. So it just denies me complete access to powering up the module. Sends ASCII string back. So then I will set some module parameters, so it'll allow me to power up here. I'm kind of lazy, so I'm just going to copy and paste from a text file. And then it sends back OK. So the command was accepted, and now let's try to power up again. It says OK, so my module should be enabled. And I can show, probably should have showed this before, to show that it actually populated data. But you can see on my watch window, I've, from the module parameters command, sent across an Excel, a work speed, a service speed, and other parameters that are useful to the machine. Also, so this is the code that that's sending this response here. It's just taking in some access data and possibly a command processor error. Let's say I put in a bogus command here, you know, FK, it's not on my system. It'll force the command processor to error out, and then it will send me a command that it is invalid and reset the command processor. In here, it's a pretty simple code. If my access data coming in says to send reply OK, I simply create an OK string with an end of line feed, which is just a carriage return in line feed, to send back. And then here, if I have command error coming in, it will send this string error invalid command, which we saw pop up here. So pretty simple. Just handling different commands. Also, I wanted to highlight earlier, Kevin was showing how you would edit those commands. And if you look in the Comm Toolbox under the command processor, you go to the help, down here, it gives you a few examples of commands. So a move relative with a few different parameters coming in, how to calculate that value in case you didn't write it down when he was explaining it, and how to use these this get parameter function that we have created to parse the data from this command coming in into your machine data structure for relevant information to your machine.
And Hunter, on that example you were showing in the web interface, could you explain that a little bit?
Example, this example web interface?
Yes.
So this socket applet, something that we developed, it's pretty simple. Just creates a socket connection for the specified port and the specified address. It's just showing that other interfaces can also connect with it. You don't need Visual Studio or Visual Basic, about anything works. And also, if another part of this command on a different port here, 50,009, if you want that monitor data, I set up another command called getStatus. I guess that is the wrong channel, never mind. It was 50,008, getStatus, and it will send back an ASCII string of data containing relevant position, speed, and such. As you can see, it's not pretty and parsed out like the Visual Studio and Visual Basic code was, but you can get the same information about the access across in a different way.
Sure, but once again, this is completely what a customer had specified they requested the response to look like, so that their software itself could understand and parse that string. So it's very flexible. How many commands or how many parameters within a command have we tested?
We've tested up to passing 100 parameters across. Scan times do not peak too terribly. We've tested it with sending 4 commands with 100 parameters apiece every few seconds, and still have had the task time under 20 milliseconds parsing these commands as fast as it possibly can. So you can get pretty good performance even with multiple channels handling multiple incoming commands.
Okay, very good. I think there's some more questions we'll try to answer now. Yeah, there's a question. Go ahead, Hunter.
Yeah, it would work exactly the same coming from a rock.
Can you read the question?
Oh yeah.
Sure.
The question is, would these techniques be used if you're using a Rockwell controller to send ASCII commands to the Yaskawa controller? Basically, it would work exactly the same. Specify the Yaskawa controller IP address and port number to send ASCII commands, and the setup should be exactly the same as a Visual Basic or Visual Studio code.
Okay, good question. Also, there's one that asks, would there be any issues using the Modbus features built in at the same time with the Comm Toolbox library? And no, there would be no problems, because the controller can handle these multiple protocols at the same time. It's always been doing that, even before the introduction of a command stringing possibility. It can handle the data between MotionWorks IEC and the controller at the same time as a web server is up, at the same time as Modbus, Ethernet IP are communicating. So these are just other communications channels that are open. And in fact, within the IEC application layer here, and within the Y-device-com firmware library, there was the possibility thus far to open 16 simultaneous sockets. For various reasons within an application we worked on recently, where they wanted to have 1 socket per axis, we increased that limit up to 64 sockets possible from just the Y-device-com portion of the controller's capabilities. In addition to everything else with Modbus. I think overall, I forget if it's 128 sockets can be open, or it's either 128 or 256. I forget which, but that includes files that the controller has open and access to, and also, let's say, an Ethernet communication channel as well. Have a good day, everyone.